So let's resume. This my great pleasure to introduce our second speaker of this brag, who is Daniele Faenze from Université de Bourgogne. He will speak on COBOL and GOPL varieties.
So I was saying I was very happy to be here and to present this story. First of all, a disclaimer. So this is about some very specific kind of examples. So some exceptional geometry going on here. So I'm afraid you will not see super general theorems. It's more like explicit and specific examples that happen in a very peculiar situation. So this being said, I will try to give you, first of all, one super specific example, then a kind of meta theorem or recipe to produce more examples, and then if we have time, another example. So this is a bit about examples. So let me start with this, so maybe one, okay, will be here, will be done. Section 2 is a bit more hopeful, and section 3 is, if miracle happens, we will get to section 3. So section 1 is about COBOL, cubics, and quadrics. And here I will try to give you the flavor of the main, so the flavor of our main constructions, and with the let's say the most classical example of this story, which is this COBOL cubic. And here I'm reading because I'm what I do here is listing a partial list of people that whose work I will freely use and in the next minutes. So these people, there is Sturmfels, there is us, but there's also Boville, there is Ortega, Dolgachev. Well, let me stop here, but there are more people, and let me try to give you some kind of summary of well-known stories. So one is about COBOL, and of course there is COBOL and GOPL, but you know that. Okay, so the story begins with COBOL, Arthur COBOL. He found a very nice hypersurface. So it's a very special cubic that has a very funny behavior. Let me try to explain what it is about. So let's say you start with a an abelian surface. Let's say that A is the Jacobian of a curve C of genus 2, for instance. Okay. And then you have theta. You have theta divisor on A. So what is theta? Actually, you can think, okay, so it's a divisor. So it's an element of Picard group of A or of J. So J is line bundles on C, right? So theta, you can think of theta as those line bundles. Okay, there's a little twist here because I'm using Picard 1, so line bundles of degree 1. So this C is C2 here, just means that it has genus 2. And, you know, these are in principle more like line bundles of degree 0, but you can move to degree 1 just by adding a point. And so these are those line bundles that have a section. This is a so-called theta divisor, and it's a way to polarize, standard way to polarize this torus, which is now an abelian surface. And this theta is an ample divisor. It has theta square is 2. And if you try to embed now this A into some projective space, you can use theta or multiples of theta. So you know that 2 theta is not very ample. And actually, the image of A with the, let me write 2 theta dual. I mean, if you use this linear system to send the abelian surface somewhere, what you get is our beloved Kummer surface, right? But then this map is not an embedding. But 3 theta is an embedding. And A into 3 theta then is so the image is a surface of degree what? This square, so 9 times 2, 18. So if I hope that everybody in this room loves abelian surfaces, yeah. But if you want to see an abelian surface like with its equations, it is not so easy, right? I mean, you have this thing, but okay, but what is the equations of A? And that's what Coble did. So Coble found a cubic inside this one, this P, what is it? P8, P7. Inside P7. Wait, no, not P7, P8. I'm always off by 1 in this projective story. Yeah, Coble found a cubic in P8, which is singular along A. The singular locus is precisely A. And actually, so this way you have the equation of this cubic, which is, by the way, very simple. And if you take partial derivatives of this equation, then you get some quadratic equations, which are exactly the equations of A under the embedding 3 theta, right? So this is nice. And, also people studied a lot this situation to understand whether this was scheme theoretic, and it is scheme theoretic, it is even ideal theoretic, and so on. This is as good as you can dream of. But then the question is, okay, is this Coble cubic related to something different? Is it interesting for some other reason? And the answer is yes, because this linear space where this cubic lives has it's not a random linear space. It is shows up for other reasons. So let me discuss vector bundles on C. On C, the C2. So we have this. Let me write use the usual notation. This notation here is what people call the moduli space of semi-stable semi-stable vector bundles of rank 3 on C with, so I write like this, it's the moduli space, it's S equivalence classes of such. And this S here stands for special, so it's something about the determinant, vector bundles E. And the determinant should be trivial. And when you have this moduli space, then also this moduli space is a kind of nice object. It's a Fano variety with nice singularities and so on and so on. It has dimension 8. And also of this space, maybe we would like to have some equations, some explicit equations. Well, that's a bit more tricky, but what one can do in this case is to use the theta, so-called theta map. There is a theta map that goes from here to, well, this time is 3 theta, not dual. So you take a bundle and you send it to, the set of it's a kind of similar definition as here, but this time is twisted with E. So E tensor L should have sections. So yeah, you take this guy and you look at the line bundles over here which have this property, and this form a subvariety of pick 1. So it's a divisor in this surface, in the same surface, and it turns out it's a divisor of class 3 theta. Okay, this 3 is the same as this. You could do this for any rank, and there's a theta map of that kind, which gives you actually a polarizing divisor of this guy. So when you have O1 here, you pull it back, and you get a polarizing divisor for that guy. So yeah, this is nice. And in general, this map, by the way, is quite unknown, the behavior of this map. Some people studied this map in general, I mean for any curve, in any genus and with any rank, but we know essentially nothing about it. One thing we know is for this case, genus 2 and rank 3, we know that this map is actually a morphism, otherwise it would be only a rational map. It is a morphism, and not only that, it is a 2-to-1 ramified cover. It's a finite map of degree 2. Yeah. Right, and then the conjecture that was a conjecture for some point, and then it was proved by Ortega, is that, okay, you have this guy here, this P8. Maybe I should call this P8 dual, right? Because there's a dual here. So we have this P8 and this P8, one dual to the other. And the conjecture was that there is a relation between the cobalt and this guy. And actually, what is true is that the branch locus of theta, so the branch locus here is a divisor in this P8, is projective dual of the cobalt. So you have this fancy, strange cubic whose singular locus is this surface, and if you take projective dual, you get the branch locus of this theta map, which is interesting for some other reasons related to moduli of bundles on a curve. Okay? This was kind of the starting, why we got interested in this. We thought that this was some nice geometry, and we tried to, understand better the picture here. And then we discovered that some people started describing this cobalt in a nice way. I mean, so far the problem is that I didn't give you the slightest hint of how to construct this COBOL, right? Now I will tell you how to construct this COBOL. So how to get C. And to get C, we use something which is apparently completely unrelated to cubics or abelian surfaces or anything. So we start with a vector space of dimension 8. And I take this exterior power, so I take alternating 3 vectors on V8, and I take a vector here, an element of this vector space. And so our P8, no. I'm sorry, I always get confused with 8 and 9, so I hope you forgive me about this. I start with a vector space of dimension 9 and a 3 vector in 9 dimensions. And yeah, so the P8 I want to make here is projectivization of this space, but I want to see this vector in this, the space of trivectors this way. Of what? Of omega 2, 3. This is just natural identification using, I don't know, Euler's sequence or something, or Bott theorem if you're a bit more sophisticated. And yeah. Okay, great. If you are a foliation man, that's your view on that. Yeah. And then this one, you can also think of, let's say, maps from here to here. So, because this is omega 2, then this is a wedge 2 of something. So this is maps from here to here up to taking one part of the wedge to the left of duality here, but alternating maps, alternating morphisms. So if I give you V, then you get an alternating morphism, this over P8. This is always given by V. And good. And so this means that if you look at a fiber over a point of P8 of, shucks, over a point of, I'm sorry, with 8 and 9 I will never make it, over a point of P9 of this, of P8 of this, of this map, then this is rank 8 vector bundle, right? And this is a 8 by 8 skew symmetric map. At every point you get an 8 by 8 skew symmetric map. And then this 8 by 8 skew symmetric map has a Pfaffian. Maybe you know that when you have a skew symmetric matrix, then its determinant is the square of something, and this something is called the Pfaffian. Yeah. So you have a Pfaffian 8 of this guy, which is a cubic equation. And the COBOL is just the vanishing of this Pfaffian. And what is nice about this construction is that the singular locus appear now kind of, yeah.
Who is tau again?
Tau. Oh, the tangent bundle. I'm sorry. The tangent bundle.
P8 or P9?
Pn. P8. Yeah. more questions? Please go ahead. At some point there will be P7, maybe. So, yeah. Right. So what is nice about this story is that when you have such skew symmetric, a morphism of vector bundles like this, then you can take its determinant, Pfaffian, and so on. But you can also look at the points where the rank is still lower, right? The determinant is where the rank is not maximal, but you can go down with the rank to smaller loci. And because the map is skew symmetric, then you jump from rank 8 to rank 6. Okay? And then you can take the Pfaffian 6. And it always happens with degeneracy loci of morphisms that the smaller rank locus is within the singular locus of the bigger rank locus. Yeah. So if you look at the vanishing locus of 6 by 6 Pfaffians of this thing, classical computations with determinantal varieties tells you that this has codimension 6 in P8, and so it is a surface. And this surface is just the singular locus of C, so it's just A. So naturally this cubic is singular, and it's naturally singular along the surface, and it turns out the surface is just A. So this is a kind of a way to produce this Coble cubic from wedge 3. And
You mean that choose the expected dimension of something defined by the 6 by 55 and 8 by 8 form. Is that?
sorry, I didn't. Again?
You said that this computation of the dimension of
Yeah.
PF6,
Yeah.
choose the expected dimension.
Yes. 2 is the expected dimension. So it makes it expected, as you say. This cubic is no longer a random cubic, but a cubic which is a determinantal or Pfaffian, and then its singular locus naturally described as inner Pfaffians, and these inner Pfaffians have such dimension expected, and it is actually the true codimension, and yeah. Good. Right, so this is good when you want to compute moduli spaces of this cubic, of these cubics, which is in principle what we would like to do. Now we know that these cubics depend on a three-dimensional, so a alternating 3 vector. Okay. And then to compute the moduli space, actually, what one does in this situation is to find a smaller space where things really happen. This smaller space is what people call the Cartan subspace. Cartan subspace is a kind of analog of Cartan subalgebra. Here, what we have here is that, so if I take the datum that I have there, this wedge 3 of V9, then I would like to act to compute moduli space with SL9. Okay. So Cartan subalgebra appears when you let algebra act on itself with adjoint representations, as we learned in the thesis of Chris. But in this case, it acts on something different. So you don't speak of a Cartan subalgebra, but rather a Cartan subspace. So this is a subspace C in this one. Sometimes I just call this just V, and consists of points with closed orbits, closed G orbit, and it has this feature. It has the main feature is that if you look at invariance, so if you want to compute moduli space now of these cubics, what do I want to do? I want to take this GIT quotient, right? So I take the polynomial ring over this, and I take invariance for SL9, okay? And the Cartan algebra has this nice property that if I take C of wedge 3 of V9, well, of V, let's say, and I take invariance, then this one is isomorphic with a much smaller space and invariant for a finite group. And here, W is a Weyl group. In this case, so yeah, it is just defined as a normalizer of the Cartan subspace. So everything that fixes the Cartan subspace modulo everything that doesn't change, doesn't move, doesn't act at all on the Cartan subspace, the centralizer. So you get a group acting on C. Yeah. And actually this group is finite. And yeah. So this story here says that the moduli space of V mod SL9 is isomorphic. The GIT quotient is isomorphic with C, a much simpler quotient, yeah, by a finite group. W is finite. Actually, W is a complex reflection group. I mean, it's generated by reflections. These reflections are what some people call pseudo reflections. So these reflections have a fixed hyperplane, but on the orthogonal subspace, the other eigenvalue is not necessarily -1. It's a complex root of unity. So that's why they call it pseudo reflections. Right. So, okay. So these are Kobo cubic. I told you how to get them. I'm telling you that the moduli space is this quotient. Yeah, this quotient, and that this quotient can be realized as a quotient by a finite group. Yeah. And then what we would like to do is to do Gopel varieties. So the Gopel variety is essentially the following. So we have some hypersurface parameterized by something special, like Kobo hypersurface. And we are considering moduli space of such hypersurfaces, okay? And we want to have, again, a kind of model of this moduli space, right? So what we do is we take the coefficients of, we start with this guy, this big V, and we go to S3 of V8. We take a vector here and associate the Pfaffian 8 of V. It's a cubic. This is not a linear map. This is actually a polynomial map of high degree. In this case, it's given by degree 4 polynomials. I mean, the coefficients of the cubic are degree 4 polynomials in the coefficients of V. Okay? And yeah, right. And then because of this story here, we move to the Cartan subspace to make the problem smaller. We restrict this to C. which means roughly that we don't look at the coefficients like in general, but only those that are really meaningful, yeah, those that allow for the same quotient, okay? And we go somewhere here to a much smaller space of the space of cubics, because many coefficients will not show up. And this space here we call, sorry for the mismatch, this has nothing to do with the previous theta m, but we have to respect some traditional notation. And this is actually the span, the linear span of what you get here. And this turns out to be a Macdonald representation of W. So actually, you can forget about Macdonald. It's just a representation of W, which, by the way, is a special kind of representation. But anyway, and this is W invariant. And then we consider the linear map. No, sorry, not the linear map. The linear system associated with this stuff. And we try to compute the image of gamma, because this image of gamma is a version of the moduli space of our problem, of our Cobo cubics, for instance. And yeah, so what people found in this particular case is that
You say that I'm confused. So when you projectivize the action on the
yeah,
you get the trivial action. You're saying that we can identify with C over W? Is that it?
C over W. Yeah. No, when I projectivize, I just lose, I'm just saying that I can acquire some base locus. This is the same map as here, only it's restricted to a subspace, and therefore I will not hit. So this space here is where the coefficients of this cubics land, okay? And if I restrict to the subspace, I will hit less coefficients, so we'll have a smaller dimensional subspace, okay? And I will lose the invariance for SL, but keep the invariance for the finite group.
I'm trying to understand the sentence. You said that the image was a version of the moduli space.
Yeah. The image of gamma is maybe I should rather call it a Hilbert scheme. It's a version of Hilbert scheme of Cobo cubics, and this image is equivariant for W. Yeah, it has a W action. Yeah. So, for instance, in this case, the idea is that this image should be an interesting variety. For instance, in this case, so here G is, by the way, is what people call G32, some complex reflection group in Shepard and Todd list. Never mind. And C has dimension 5. Theta. C has dimension 4. Theta M has dimension 5. And the image of gamma is what people call the Burckhardt. Now I have to spell it. Maybe there's a T here, not sure. Quartic. And this is a quartic in P4, which has maximal. It's a quartic that realizes the maximal number of double points, which is 45. Okay, so this is the picture. Again, we have some hypersurface, this cubic, parameterized by something related to representation theory. And when you compute the coefficients of this hypersurface, we get something which is invariant for a finite group, actually a complex reflection group. And this gives rise, by looking at the coefficients, to some moduli space or Hilbert scheme of Cobo cubics, which lives inside a representation here, and which is a very special gadget, in this case a quartic in P4, having a high number of double points, incidentally maximal number of double points that a normal quartic can have. A quartic with isolated singularities can have at most such number of double points. Yeah, so this is the story. And actually, I'll leave it here. And actually there's a second bit of the story, which is what I'd like to explain now. So actually, our point of view is based on all this stuff. What can you do to find more interesting varieties, maybe related to moduli spaces of bundles and so on and so on? So is this part 5? So this is more cobbles from the same data. So our approach actually is the following. Yeah.
Gopal variety is which one? C?
Yeah, Gopal variety is the image of gamma.
But it's also called Burkhardt.
In this case, it is the Burkhardt.
Okay, so there's more general.
Yeah, so this is what, we call Gopal varieties, Hilbert schemes inside Macdonald representations of Cobo type hypersurfaces. Okay? So what I'll do now is to give you some more Cobos. And then the idea is that for each Cobo, you can get some Gopal. Maybe it's some nice variety, maybe not. And then maybe I'll tell you what is the framework to get more examples of this kind if you want to play.
So the Gopals are more or less moduli space of Cobals.
Right. Or Hilbert schemes of.
And from this point of view, is there a nice notation for these 45 points of similarities of the
There is. I would not enter into that, but yeah. Okay. So our main point is that, okay, from this data, V, we could construct this Cobo this way, but we thought, okay, maybe there's more stuff that you can construct starting from the same data. More stuff, in particular, inside other homogeneous spaces rather than Pn. Maybe some Grassmannian and so on. So let me tell you quickly what this gives. For instance, so again, you start with V in wedge 3 of V9. And now you see this one as maybe H0 again, but of wedge 3 of quotient bundle. So here Q is quotient bundle of how do I call it? G3 V9. You get a rank 6 Okay? Here I just identified V with this space of sections. Now I identified with this other. It's as natural as the other was. Let's see if it gives something. And yeah, so it does. And what is it? So it gives, okay, it gives, yeah. You look at, for each x in G3V9, you look at Vx, let's say, will belong to wedge 3 of Qx, right? I mean, I just have wedge 3 of V9. I restrict this to, I pass to the quotient, and I think of the 3 vector as an element of this space, of this fiber, okay? And then I look inside wedge 3 of C6, just a fixed vector space. The orbits, there are finitely many orbits here. Orbits for GL6. And I have Y1. Here the index indicates the codimension of these orbits. Oh, yeah. So this is the principle of orbital degeneracy locus. It means that you have some orbits in the fibers of your vector bundle, and then you can look at the points you can look at the points of your variety such that V, your initial data, when you look at X, it lies in this orbit. And then you get some orbits of the same codimension, some subspaces of the same codimension, subschemes of the same codimension of G. Right? You get Z1, a hypersurface, which is actually a quadric section of the Grassmannian that will contain Z5, is it right? That will contain Z10. Okay, and this has codimension 10 inside G3V9. So now you will help me. This one has dimension what? 3 times 6. Yeah, so this one has dimension 8. Okay? And the theorem we have is that Z10, okay, for general V, Z10 is the singular locus of Z5. Z5, okay, $1 million guess, singular locus of Z1. And Z10 is actually isomorphic with SU, again the same, a curve here, a curve C2 of genus 2, again of rank 3. But this time it's not the degree determinant 0 vector bundles. It's the vector bundles whose determinant is a single point. Okay, so this parallels in some sense what I've been showing you at the beginning, this duality story, where there was a vector bundle, modular space of vector bundles coming into play. There was a branch locus. This time there's no branch locus because the linear system is just very ample. So for odd determinant here, it will be very ample, and also this guy will be smooth. It's a smooth Fano eightfold. And this guy is precisely the singular locus of the singular locus of this Cobo quadric. Yeah. So it's a bit more nested than the original statement because it's the singular locus of the singular locus. But you still get a modular interpretation of that guy. Right, and then we get interested into computing Cobo. This is our Cobo quadric. We call this guy Cobo-like quadric. And then our goal would be to compute the GOPL. So the GOPL would be another GOPL for another kind of Cobo, but starting from the same guy and landing into, so maybe another gamma prime to another.
I'm confused. You're saying that Z1 is a quadric?
Yeah.
Quadric hypersurface?
Quadric hypersurface.
Isn't the singular set of a quadric hypersurface a linear space?
It's a special quadric. It's a linear. If you wish, it's a linear It's a linear subspace. Then it will cut the Grassmannian in a strange way. It's a quadric in the Grassmannian. When you cut it, you get a funky linear section of the Grassmannian, whose singular locus is this guy. Yeah, and then we have this time this would arise from wedge 3 of V9 mapping through some gamma prime to H0 this time over the Grassmannian of O2. The Cobo quadric, the coefficients will be here, and passing to the Cartan space, it will give some Cobo story, and our goal is to compute this thing. And this is where the project is a bit stuck, because we still don't know what's the image of this one. We only know that the Cobo has a modular interpretation, and we still don't know what the GOPL exactly is. We know something. We know that this one is, we know the gamma prime is birational onto its image. We know something about the base locus, but we don't know yet what are the singular loci, what is the singular loci, locus of the image, and so on and so on. So that's the part of the project which is still in progress. Okay. And now, so I have around 5 minutes, I don't know, but let me give you the general recipe of how to obtain this kind of stuff. Or at least a meta theorem. Yeah. Yeah, the abelian variety is there. The abelian variety and the curve and some special point on the curve are there, but it would take some time to understand where they come from. There's a whole story about the linear subspaces that are contained in this guy, linear spaces of a certain kind, which are called Hecke planes. These Hecke planes are related to the moduli space that I mentioned before, and so on. There's a full geometry that has to be explained in order to answer that question. But yeah, the upshot is that this wedge 3, it's related to abelian variety, essentially through Heisenberg groups. There's a Heisenberg group appearing directly from the Cartan subspace, and that tells you that there should be an abelian variety coming into play, and also there is polarization and so on. But yeah, it's a bit long story. Okay. But anyway, so yeah. So let me tell you roughly how this goes. So a general recipe to produce more examples of this kind in the hope that they are interesting. So actually, where the hell does this wedge 3 come from? Actually, it comes from grading of Lie algebra. Of simple Lie algebra. Okay, so you should take a cyclic, so you take a G, a simple Lie algebra, and I don't know, maybe P, a prime number, and construct a Z of a P cyclic grading of G. So this may look a bit fancy if I tell it that way, but it's not that hard, because when you have G, maybe here. When you have G, you should choose a root, okay? You should color a root. No. This one. You should color a root, and when you write alpha, when you write any root as a sum of mi alpha I with alpha 1 alpha r fundamental root and mi integer, then if you choose I0 here, equal to 2 actually in the Bourbaki notation, then if you look at mi0 congruous to, I don't know, k modulo p, the prime you choose, and then this gives you, then it means that alpha lies in the k part, of the grading. Okay, you have a cyclic grading, and the k part is the set of roots whose coefficient with respect to the root you chose is congruous to k mod p. Okay, so for instance, in this situation here, what you get, the one that I chose on the board, I draw on the board, will give you. So this it goes back to Wimberg. All this story. Maybe let me write his name. Wimberg. For instance, here you get E8 for p equals 3, and yeah, that root is the part 0 is SL9 plus wedge 3 of V9, this is G1, and then there is wedge 6 of V9, this is G2. So each time you have a simple algebra with a cyclic grading, you get this thing, and the part in degree 0, G0, such that Lie group, such that its Lie group is just G0, will be a semi-simple Lie group, and it will act on G1, which is our V. And this has a Cartan subspace. So in principle, you can do, so in principle already you know that V mod G0 will be isomorphic to Cartan subspace mod W, where W is the Weyl group exactly that I defined before. So the normalizer module the centralizer. And this W is always a complex finite complex reflection group. Right. So this is the moduli story. And what is the COBOL story? The COBOL story is that now you want to choose a G0 homogeneous vector space variety, G0 rational homogeneous variety. So this is then choose Z a G0 homogeneous variety. For instance, we chose Pn or the Grassmannian and so on, where V in G1 gives a hypersurface, which I call it COBOL. And look at theta m, the MacDonald representation induced by coefficients induced in H0, hypersurface of, say, of degree delta. So we had a COBOL cubic, a COBOL quadric, and so on. And then in Z, in the G0 homogeneous space, you look at the coefficients of the COBOL inside here, right? And this will be a MacDonald representation, and then you study gamma, which will go from P of C to P of theta. This M, usually we just denote the dimension of that representation. And play, that's our project. You choose a group, you choose a root, and you choose a there are a lot of choices. But we hope that for some choices, there will be something nice. And the part 3 of my talk will be for some other time. I plan to give you another example, actually, with another choice of group. You see, we tend to choose exceptional groups because they give some nice varieties, and so on and so on. But there are also some non-exceptional groups that play a nice role. This also has some applications to tropical compactifications. It has applications in more arithmetics. For instance, Bhargav Bhatt has been looking at this story, not this one, but a similar one on any field and then he gets something. But yeah, so let me just advertise that this may give something interesting, and leave the remaining examples for the discussion. Thank you.